In today's documentary, we're discussing the inventions of Nikola Tesla, a visionary whose ideas transformed our world and continue to shape our future. From humble beginnings to revolutionary breakthroughs, Tesla's extraordinary mind gave us technologies we now take for granted and concepts so advanced, some are only now being realized. Let's begin our documentary. Arc lighting system. Imagine the streets of America in the late 19th century. Gas lamps cast their yellow glow as horse-drawn carriages clatter by. This is the world that welcomed young Nikola Tesla, a Serbian immigrant with ambitious dreams. His first significant professional achievement wasn't creating something entirely new, but rather improving what already existed: the arc lighting system. Arc lights were the first practical electric lights, producing illumination by creating an electric arc between two carbon electrodes. They were harsh, noisy, and inefficient by modern standards, but revolutionary for their time. Tesla saw beyond their limitations. He meticulously enhanced their efficiency, demonstrating even in these early days his extraordinary grasp of electrical principles. This work might seem modest compared to his later achievements, but it represents something important about Tesla's genius: his ability to see possibilities for improvement where others saw finished products. His enhanced arc lighting system illuminated not just streets, but the path of his career as an electrical innovator. Alternating current AC electrical system. As Tesla continued his work, he became increasingly convinced that the American electrical system, built around Thomas Edison's direct current, DC, was fundamentally limited. Direct current, where electricity flows continuously in one direction, worked fine for lighting small areas, but couldn't efficiently travel long distances. Imagine trying to deliver water to a distant city through a pipe, but the water keeps losing pressure along the way. That was the problem with Edison's DC system. Generating stations needed to be built every few blocks in cities, making rural electrification nearly impossible. Tesla envisioned something radically different: alternating current, where the flow of electricity periodically reverses direction. At first glance, this might seem like a mere technical difference, but the implications were revolutionary. Think of alternating current as having a unique property: it could be transformed. Just as a lever allows you to lift heavy objects with less effort, transformers allowed Tesla's AC to be stepped up to high voltages for long-distance transmission with minimal loss, then stepped down to safer voltages for home use. This seemingly simple innovation made it possible to generate electricity at distant locations, like waterfalls or coal plants, and transmit it efficiently to cities and eventually rural areas. Edison fought fiercely against Tesla's alternating current, even resorting to public demonstrations electrocuting animals to portray AC as dangerous. But Tesla remained steadfast, believing in the superiority of his system. This period became known as the War of Currents, and its outcome would determine how electrical power would be distributed worldwide for generations to come. Polyphase system. While the debate between AC and DC raged, Tesla was already developing something even more sophisticated: the polyphase system. To understand this breakthrough, imagine a team of rowers on a boat. If all rowers stroke at exactly the same time, the boat moves forward but with periodic surges and lulls. But if rowers time their strokes to overlap, the boat moves forward with continuous smooth momentum. Tesla's polyphase system worked on a similar principle. Instead of a single alternating current that rises and falls in a simple pattern, multiple currents operate with timed offsets, creating smooth, continuous power. This wasn't just an incremental improvement, it was a fundamental reimagining of electrical systems. The world got its first dramatic glimpse of this technology at the 1893 Chicago World's Fair. The White City, as the fairgrounds were known, blazed with electric light powered entirely by Tesla's polyphase system. Visitors who had never seen electric lighting stood in awe as Tesla's technology illuminated the night, giving America a vision of an electrified future. This wasn't just a technical demonstration, it was a transformative cultural moment that helped people understand how electricity could reshape their world. Today, this same polyphase approach remains the foundation of our global power grid. a lasting testament to Tesla's foresight and engineering brilliance. Induction motor. If the polyphase system was Tesla's symphony, the induction motor was its most beautiful movement. Patented in 1888, this device would become the workhorse of global industry for generations to come, powering everything from factory machinery to household appliances. The beauty of Tesla's induction motor lay in its elegant simplicity. Previous electric motors required physical electrical connections to their moving parts through components called brushes and commutators. These parts constantly wore down, creating maintenance headaches and efficiency losses. Tesla's design eliminated these troublesome components entirely. Instead, his motor used the rotating magnetic fields of his polyphase system to induce electrical currents in the motor's rotor, hence the name induction motor. With no physical electrical connection to the moving parts, Tesla's motors were more reliable, efficient and durable. To appreciate the impact of this invention, consider the factories of the early industrial age. Noisy, dangerous places filled with steam engines driving complex systems of belts and pulleys to power machinery. Tesla's induction motor offered a cleaner, safer alternative. Compact electric motors that could be placed exactly where power was needed. More than a century later, when you hear the quiet hum of your refrigerator or feel the vibration of your washing machine, you're experiencing the direct legacy of Tesla's induction motor. Even many modern electric vehicles use advanced versions of Tesla's induction motor design, a fitting tribute from a company that bears his name, Tesla Coil. By 1891, Tesla was exploring territory that seemed to border on the magical. His creation, the Tesla Coil, produced spectacular displays of artificial lightning that both entertained and educated audiences about the possibilities of high-frequency electricity. The Tesla Coil is essentially a high-voltage, high-frequency transformer circuit. Imagine a device that takes ordinary household electricity and transforms it into miniature lightning bolts that can leap through the air. During public lectures, Tesla would often stand in the midst of these electrical discharges, the currents passing harmlessly over his body as audiences watched in astonishment. But the Tesla Coil wasn't merely a theatrical device. It represented a breakthrough in our understanding of resonant electrical circuits, systems where electrical energy oscillates at specific frequencies. This principle of electrical resonance would prove crucial for the development of radio technology and wireless transmission. When you adjust the dial on an analog radio or use your smartphone's wireless capabilities, you're benefiting from principles that Tesla demonstrated with his resonant transformer. The Tesla Coil remains one of his most visually dramatic inventions, still recreated by enthusiasts and educational institutions to demonstrate the power and beauty of electrical phenomena. Resonant transformer technology building on the principles demonstrated in his Tesla Coil, Tesla continued to develop resonant transformer technology throughout the early 1890s. This work focused on the phenomenon of electrical resonance, similar to how a swing moves higher when pushed at just the right moment, or how an opera singer's voice can shatter a glass by matching its natural frequency. Tesla discovered that carefully tuned electrical circuits could resonate with each other, creating powerful effects with remarkable efficiency. He applied this knowledge to create transformers that could achieve high voltages without the bulk and limitations of conventional designs. This resonant approach to power conversion isn't just of historical interest. It lives on in many modern electronic devices. When you place your smartphone on a wireless charging pad, you're using inductive coupling principles related to Tesla's resonant transformer work. Modern power supplies in computers and other electronics often use resonant conversion techniques to achieve greater efficiency in smaller packages. Tesla's work on resonant transformers demonstrates how fundamental discoveries in electrical science continue to find applications long after their inventor's time, evolving to meet the needs of technologies that would have seemed like fantasy during Tesla's lifetime. Wireless lighting. Among the most dramatic demonstrations of Tesla's electrical mastery was his ability to make light bulbs glow without any wired connection. During his famous lectures of the early 1890s, Tesla would often hold glass tubes filled with gas that would illuminate brilliantly in his hand, powered solely by the electromagnetic fields he had generated in the room. Imagine the astonishment of audiences who had only recently become accustomed to electric lights requiring wires. Here was Tesla, seemingly defying the known laws of electricity, making light appear as if by magic in empty space. The principle behind this spectacle was electromagnetic induction, the same phenomenon that powers wireless chargers today. Tesla's high-frequency fields induced currents in the gas-filled tubes, exciting their atoms and causing them to emit light. This wasn't just showmanship, it was Tesla demonstrating his vision of a wireless future. He believed that eventually homes could be illuminated without the need for wires woven through walls, a concept that seemed revolutionary then and still captures the imagination today. While we haven't fully realized Tesla's vision of wireless home lighting, the principles he demonstrated have found applications in everything from wireless charging technologies to RFID systems used in contactless payment cards. Neon and fluorescent lighting. Tesla's experiments with gas discharge tubes led directly to what we now know as neon and fluorescent lighting. While exploring how different gases respond to electrical stimulation, Tesla discovered that various gases emit distinctive colors when energized by electricity. At the 1893 World's Fair, where his polyphase system powered the event, Tesla also demonstrated glass tubes bent into names and shapes that glowed with colorful light. He had effectively created the first neon signs, decades before they became a staple of urban landscapes. More significantly, Tesla's work laid the foundation for fluorescent lighting technology. Unlike Edison's incandescent bulbs, which produce light by heating a filament until it glows, wasting much energy as heat, fluorescent lights use electricity to excite gas atoms that then emit ultraviolet radiation, which causes a phosphor coating to fluoresce or glow. The impact of this technology has been enormous. Fluorescent lighting eventually offered efficiency 4 to 6 times greater than incandescent bulbs, dramatically reducing energy consumption for lighting worldwide. Every office building illuminated by fluorescent lights and every city street brightened by the distinctive glow of neon signs carries forward Tesla's legacy of gas discharge lighting innovation, X-ray research and early imaging. In the mid-1890s, Tesla was exploring the effects of high-voltage vacuum tubes work that led him into the realm of what we now call X-rays. Remarkably, Tesla was conducting experiments with these unknown rays in 1894, before Wilhelm Röntgen's formal discovery of X-rays in 1895. Tesla noticed that photographic plates near his high-voltage experiments were becoming fogged, suggesting some form of invisible radiation was affecting them. He began taking systematic photographs using this strange radiation, even creating images of the bones in his hand. The same demonstration that would later make Röntgen famous. Upon learning of Röntgen's publication, Tesla congratulated him and intensified his own research, quickly making several improvements to early X-ray technology. He recognized both the potential benefits and dangers of these rays, warning about the need for proper shielding and limited exposure safety concerns that wouldn't be widely appreciated for decades. Though Tesla didn't receive primary credit for the discovery of X-rays, his early work and subsequent improvements contributed significantly to this revolutionary medical and scientific tool. Today, every hospital's radiology department stands as a testament to this remarkable branch of Tesla's wide-ranging investigations. High-frequency therapeutic devices. Tesla's fascination with the effects of electricity on the human body led him to develop various high-frequency therapeutic devices in the mid-1890s. He believed that carefully controlled electrical frequencies could provide health benefits without the harmful effects sometimes associated with electrical exposure. These weren't merely the questionable electric cure devices common in the era's medical quackery. Tesla approached this work with scientific rigor, carefully studying frequency, current, and application methods. He developed devices that delivered controlled high-frequency currents to the body, reporting benefits ranging from improved circulation to pain relief. While many of his specific therapeutic claims remain unverified by modern standards, Tesla's work did influence the development of various legitimate electrotherapy treatments still used today. modern transcutaneous electrical nerve stimulation, TENS units for pain management, certain physical therapy devices, and some dermatological treatments using electrical stimulation can trace part of their lineage to Tesla's pioneering investigations. Tesla's exploration of electricity's effects on biological systems represented an early vision of bioelectrical medicine, a field that continues to develop today as researchers explore electromagnetic treatments for various conditions, from wound healing to brain stimulation therapies. Radiotechnology. Few of Tesla's contributions have generated as much historical controversy as his role in the development of radio. While Guglielmo Marconi is widely credited with the invention of radio, Tesla had patented crucial elements of radio technology years before Marconi's famous demonstrations. In the early 1890s, Tesla developed and publicly demonstrated devices for wireless transmission and reception of electromagnetic signals, the fundamental components of radio communication. His patents covered key aspects of tuned circuits that would prove essential to practical radio systems. The debate over who deserves primary credit for radio continued for decades, culminating in a 1943 US Supreme Court decision that upheld Tesla's prior patents, effectively recognizing his fundamental contributions to radio technology. Unfortunately, this legal vindication came months after Tesla's death. Beyond the question of who deserves credit, what's clear is that Tesla understood the principles of radio communication with remarkable clarity at an early stage. He envisioned not just point-to-point messaging, but broadcast applications that would eventually lead to radio and television as we know them. Every time you tune your car radio or stream audio on your smartphone, you're benefiting from principles that Tesla articulated and demonstrated over a century ago, regardless of who history ultimately names as radio's primary inventor. Enhanced magnifying transmitter. Tesla's experiments with wireless transmission reached their most dramatic heights during his time in Colorado Springs in 1899, where he built what he called the enhanced magnifying transmitter, essentially a massive, enhanced version of his Tesla Coil, designed for wireless power transmission on an unprecedented scale. The Colorado laboratory became the site of spectacular electrical displays. Witnesses reported seeing enormous lightning-like discharges from Tesla's equipment that lit up the night sky. The primary coil stood 75 feet in diameter, and Tesla claimed his apparatus produced millions of volts, generating electrical arcs up to 130 feet long. The purpose of these dramatic experiments wasn't merely spectacle. Tesla was systematically exploring how electrical energy could be transmitted wirelessly over significant distances. He later claimed to have lit 200 lamps wirelessly from a distance of 26 miles, and to have created electrical effects detectable at much greater distances. While the full extent of Tesla's achievements in Colorado Springs remains debated, what's certain is that he was pushing the boundaries of electrical science far beyond conventional thinking of his time. His work there laid the theoretical foundation for his most ambitious project, the Wardenclyffe Tower, and represented a critical step in his vision of worldwide wireless power distribution. Global Resonance Detection System. During his Colorado Springs experiments, Tesla made a remarkable discovery that continues to fascinate scientists today. He detected what he believed were stationary waves, rhythmic electrical oscillations within the Earth itself. Tesla concluded that the planet has natural electrical resonances that could be detected, measured, and potentially harnessed. Imagine discovering that our planet rings electrically like a bell when struck by lightning, maintaining consistent frequencies that could be tapped into for communication or power transmission. This was Tesla's insight, decades before modern science would confirm aspects of this phenomenon in what we now call the Schumann resonances, low-frequency electromagnetic oscillations in the Earth's atmosphere. Tesla developed sensitive equipment to detect these planetary electrical oscillations, believing they could form the basis of a global communication network. He envisioned stations worldwide that could tap into these natural frequencies, allowing messages to be transmitted to any point on Earth, without the need for wires or even conventional radio signals. This concept represented Tesla thinking on a truly planetary scale, seeing the Earth itself as an electrical system that could be understood and utilized. Modern research into global electromagnetic phenomena has validated aspects of Tesla's observations, though not necessarily all of his more ambitious claims about their potential applications. Terrestrial stationary waves building on his detection of Earth's electrical resonances, Tesla developed the concept of terrestrial stationary waves, a method for using the Earth itself as a conductor for electrical signals. Unlike conventional radio waves that propagate through the air, Tesla proposed that carefully tuned electrical impulses could travel through the ground, creating standing wave patterns that could be detected worldwide. To understand this concept, imagine dropping a stone in a perfectly circular pond. The waves spread outward, reflect off the edges, and create complex patterns where waves reinforce or cancel each other. Tesla believed electrical impulses could create similar patterns using the Earth as a medium, with properly tuned receivers able to detect these signals anywhere on the planet. This wasn't just theoretical speculation. Tesla claimed successful experimental verification during his Colorado Springs work in 1899 to 1900, reporting that he had detected signals transmitted through the Earth over considerable distances. These experiments formed the foundation for his vision of global wireless communication and power transmission without the need for an extensive infrastructure of towers and antennas. While modern wireless communications took a different path, primarily using electromagnetic waves through the atmosphere, aspects of Tesla's terrestrial transmission concepts have found applications in specialized areas like submarine communications and geophysical research techniques. Wardenclyffe Tower, Tesla Tower. Tesla's vision of global wireless communication and power culminated in his most ambitious project, the Wardenclyffe Tower on Long Island, New York. Construction began in 1901, with Tesla dreaming of creating the first station in a worldwide network for transmitting information and energy wirelessly across the planet. Rising 187 feet above the Long Island landscape, the tower featured a distinctive mushroom-shaped dome made of wooden struts covered with copper. But what made Wardenclyffe truly revolutionary wasn't just what visitors could see above ground. Beneath the tower lay an elaborate network of tunnels and a shaft extending 120 feet into the earth, a critical component of Tesla's system for using the ground itself as a conductor. Tesla intended Wardenclyffe to be far more than what we would now call a radio station. He envisioned it as a facility that could transmit not just messages, but electrical power to distant receivers without wires. Imagine a world where energy generated at Niagara Falls could power devices anywhere on Earth without the need for transmission lines or local generating stations. This was Tesla's ambitious goal. Unfortunately, Wardenclyffe also represents one of Tesla's greatest disappointments. When his principal backer, J.P. Morgan, withdrew financial support around 1906, construction halted. The rise of Marconi's more conventional and commercially successful radio system further undermined support for Tesla's grander vision. The tower stood abandoned until 1917, when it was demolished for scrap during World War I. Today, the site has been preserved as the Tesla Science Center at Wardenclyffe, a memorial to what might have been if Tesla's most ambitious project had reached completion. Tesla's world system. The Wardenclyffe Tower was meant to be just the beginning of what Tesla called his world system, a global network for wireless transmission of information and power that would transform human civilization. In writings from 1900 to 1915, Tesla outlined a comprehensive vision far beyond what most of his contemporaries could even imagine. Tesla's world system aimed to provide worldwide wireless communication, including wireless telephone service, broadcasting, secure government communications, and interconnection of all existing telegraph exchanges worldwide. More remarkably, it would also enable wireless transmission of electrical energy to any point on Earth, universal timekeeping through synchronized clocks, and global navigation support for ships. If this sounds remarkably similar to our modern connected world of telecommunications, GPS navigation, and synchronized network time. That's no coincidence. Tesla had effectively conceptualized many elements of our digital infrastructure decades before the technology existed to realize them. While we've achieved many aspects of Tesla's vision through different technical means, fiber optic cables, communication satellites, and cellular networks, we still haven't realized his dream of wireless power transmission on a global scale. This unfulfilled aspect of Tesla's world system remains one of the most tantalizing what-ifs in technological history. Bladeless turbine, Tesla turbine. After the disappointment of Wardenclyffe, Tesla turned his attention to mechanical engineering, developing the remarkable bladeless turbine in 1913. Unlike conventional turbines with bladed rotors, Tesla's design consisted of smooth parallel discs attached to a shaft, spaced slightly apart. The principle behind this unusual design involves what engineers call the boundary layer effect. When fluid, either liquid or gas, flows between the discs, it naturally adheres to their surfaces through viscosity, dragging the discs along and creating rotational force. Imagine placing a playing card flat on a smooth table and blowing across its surface. The card doesn't just slide, it spins. Tesla's turbine harnessed this same principle at an industrial scale. Tesla claimed extraordinary efficiency for his turbine, and while it never replaced conventional designs in most applications, the bladeless turbine offered several potential advantages. It was simple to manufacture, durable with few moving parts, and capable of using a wide variety of fluids, including steam, combustion gases, or liquid fuels. Today, Tesla's bladeless turbine design continues to find specialized applications where its unique properties offer advantages. From pumping abrasive slurries that would damage conventional pumps to certain medical devices where gentle fluid handling is essential. Modern researchers continue to explore applications for this ingenious mechanical invention that operates on principles different from most conventional turbomachinery. Tesla's valvular conduit, Tesla valve. In 1916, Tesla patented another mechanical innovation that demonstrated his genius for elegant solutions, the valvular conduit, now commonly known as the Tesla valve. This device accomplishes something seemingly impossible. It allows fluid to flow freely in one direction while inhibiting flow in the opposite direction, all without any moving parts. The secret lies in the valve's asymmetrical geometry. The fluid path contains a series of interconnected, teardrop-shaped loops. When fluid flows in the forward direction, it passes through smoothly. But when flow reverses, the loops create conflicting currents that effectively block backward movement. To visualize how this works, imagine trying to walk through a crowded hallway. Walking in one direction, people naturally step aside to let you pass. But trying to walk the opposite way, you constantly collide with people moving against you, making progress difficult. Tesla's valve creates this same effect using only carefully designed fluid channels. This elegantly simple invention found limited application in Tesla's lifetime, but has experienced renewed interest in recent decades. Modern microfluidic devices, lab-on-a-chip technologies, and certain medical applications have adopted Tesla's valve concept where reliability, durability, and the absence of moving parts are critical advantages. The Tesla valve stands as a testament to its creator's ability to develop solutions that seem obvious in retrospect, but required profound insight to conceive. Bladeless pumps. Applying the same boundary layer principles that made his bladeless turbine work, Tesla also developed bladeless pumps between 1910 and 1915. These devices essentially operated like his turbine in reverse. Instead of fluid causing smooth discs to rotate, rotating discs moved fluid through viscous drag effects. The advantages of these pumps were significant for certain applications. With no protruding impeller blades, they could handle abrasive materials, slurries, and viscous fluids that would quickly damage conventional pumps. Their simple construction made them durable and easy to maintain with minimal wear components. Tesla's bladeless pump design demonstrates his talent for finding elegant, non-obvious solutions to engineering challenges. Rather than trying to improve existing pump designs incrementally, He took an entirely different approach based on fluid dynamics principles that others had overlooked. These pumps never replaced conventional designs for general applications, but they found specific niches where their unique properties offered clear advantages. Modern versions of Tesla's bladeless pump concept continue to be used in specialized industrial applications, where gentle handling of sensitive fluids or pumping of abrasive materials makes conventional pumps problematic. Mechanical oscillator, the earthquake machine. Perhaps one of Tesla's most legendary devices was his mechanical oscillator, a relatively small machine that could reportedly generate enormous vibrational forces. According to a famous anecdote, Tesla was testing this device in his Houston Street laboratory in 1898 when he set it to resonate with the natural frequency of the building. The vibrations became so severe that concerned neighbors called the police, and Tesla reportedly had to smash the device with a hammer to stop it. While this story has likely been embellished over time, it illustrates an important principle Tesla was exploring: mechanical resonance. Just as a child on a swing can reach great heights with small, properly timed pushes, Tesla's oscillator could generate powerful vibrations through precisely timed small impulses. The oscillator was essentially a steam-driven piston fitted with a spring carefully tuned to build up oscillations at specific frequencies. Tesla envisioned practical applications, including new types of power generators, improvements in manufacturing processes, and even therapeutic medical devices. Tesla's understanding of resonance, whether electrical or mechanical, was decades ahead of his time. Today, resonant phenomena are carefully considered in engineering disciplines ranging from civil engineering to electronics, with structures and circuits designed either to avoid destructive resonance or to harness it for useful purposes. Steam-driven oscillators. Building on the principles of his mechanical oscillator, Tesla developed more refined steam-driven oscillators in the late 1890s. These devices converted the expansive force of steam into rapid mechanical oscillations, which could then be harnessed for various purposes, including generating electricity. Tesla believed these compact power generation units could replace much larger and more complex steam engines and generators of the era. His oscillator design eliminated many moving parts found in conventional steam engines, potentially offering greater reliability and efficiency in a smaller package. While these devices never achieved widespread commercial adoption, they represented Tesla's ongoing efforts to find more elegant, efficient solutions to engineering challenges. His steam oscillators demonstrated an approach to energy conversion that differed fundamentally from the dominant technologies of his time. The principles behind Tesla's oscillators continue to influence modern engineering approaches to energy conversion and vibration analysis. Though we may not use steam-driven oscillators today, the underlying concepts of mechanical resonance and efficient energy conversion that Tesla explored remain relevant in contemporary mechanical and electrical engineering. Mechanical therapeutic devices. Tesla's work with mechanical oscillators led him to develop therapeutic applications in the 1890s. He created devices that delivered controlled vibrations to the body, believing that specific frequencies could provide health benefits ranging from improved circulation to pain relief. These weren't the stereotypical ineffective vibration belts that became common in the early 20th century. Tesla approached this work with scientific rigor, carefully studying how different frequencies affected various bodily systems. He reportedly used a mechanical oscillator on himself regularly, claiming it provided an invigorating effect. While many of Tesla's specific therapeutic claims would require modern clinical studies for verification, his approach to vibrational therapy was ahead of its time. Today, various forms of vibrational therapy are used in legitimate medical contexts, from ultrasonic treatments to vibration plates used in physical therapy and sports medicine. Tesla's exploration of how mechanical energy interacts with biological systems represents another facet of his wide-ranging genius, an ability to see potential applications of his inventions across diverse fields, from industrial power to human health. Radio remote control. In 1898, Tesla achieved another remarkable first when he publicly demonstrated a radio-controlled boat at Madison Square Garden in New York. This wasn't just any remote-controlled toy. It was the world's first practical demonstration of wireless remote control, a technology we now take for granted in everything from television sets to drones. Tesla's boat, which he called a tele-automaton, could be commanded to move forward, stop, turn, and flash lights, all controlled wirelessly from a transmitter. The audience was astonished, with some spectators suggesting there must be a trained monkey hidden inside the boat, or that Tesla was controlling it with his mind. What makes this achievement particularly impressive is that it occurred at the very dawn of radio technology itself. Tesla not only had to create the remote control system, but also develop much of the underlying radio technology that made it possible. This invention represented far more than a novelty. Tesla envisioned remote-controlled vehicles serving in warfare, reducing human casualties, and in dangerous civilian applications like firefighting. His 1898 patent is now recognized as the birth of robotics technology, establishing principles that would eventually lead to everything from industrial automation to the Mars rovers. Every time you use a remote control or operate a device from your smartphone, you're building on the foundation Tesla established with his groundbreaking demonstration of wireless control more than a century ago. Logic gates and early computing concepts. Hidden within Tesla's remote control patents from 1898 are concepts that would later become fundamental to electronic computing. To make his remote-controlled boat respond to specific commands, Tesla developed electrical circuits that performed logical operations, essentially early versions of what we now call logic gates, the building blocks of digital computers. Tesla described selective circuits that would only respond to specific signals or sequences of signals, conceptually similar to the AND, Oregon, and NOT operations that form the foundation of digital logic. These selective circuits allowed his boat to distinguish between different commands and respond appropriately. What makes this truly remarkable is that Tesla was describing these logical electronic operations decades before the formal development of Boolean logic circuits in computing. While mechanical calculating machines existed in Tesla's time, the concept of electronic logic operations was visionary. Though Tesla never pursued computing technology directly, his early work on logical circuits for selective control systems represents another example of how his thinking anticipated technological developments that would only be fully realized long after his time. Telautomatics. Building on his remote control demonstrations, Tesla developed a broader vision he called telautomatics, the science of controlling mechanical systems from a distance. He published detailed theories on this subject in 1900, essentially outlining principles of what we would now call robotics and automation. Tesla didn't see remote-controlled devices as mere novelties or toys. He envisioned autonomous machines that could sense their environment and perform complex tasks without continuous human guidance, concepts that accurately describe modern robotics and autonomous systems. He predicted that telautomatics would revolutionize warfare, industry, and exploration, allowing humans to extend their reach into environments too dangerous for direct human presence. With remarkable foresight, he described machines that could operate underwater, in extreme temperatures, or in toxic environments, applications that precisely match how we use robotics today. While the technology of Tesla's era couldn't fully realize these visions, his conceptual framework was sound. Today's industrial robots, autonomous vehicles, drones, and space exploration rovers all operate on principles that Tesla articulated over a century ago, making him a true pioneer of robotic technology. Guided weapon concepts. Between 1900 and 1915, Tesla proposed several concepts for guided weapons to various military organizations. He envisioned remotely controlled vehicles, including torpedoes, boats, and aircraft, that could be precisely directed to targets without risking human operators. These weren't mere speculations, but detailed technical proposals based on his demonstrated expertise in remote control technology. Tesla understood that removing humans from direct combat could fundamentally change military strategy and potentially reduce casualties. One of his most fully developed concepts was for a wirelessly controlled torpedo that could be guided from shore or ship. The military establishments of the time largely dismissed these ideas as impractical or too futuristic, a significant miscalculation as guided weapons would eventually become central to modern warfare. What Tesla was proposing in the early 1900s wouldn't be realized until decades later, during and after World War II, when guided missiles and other precision weapons began their transformation of military technology. Today's cruise missiles, smart bombs and military drones are sophisticated implementations of principles Tesla articulated a century ago. Electric-powered supersonic airship. Among Tesla's more speculative concepts from the 1910s was an electric-powered supersonic airship. Unlike conventional aircraft that use propellers or jet engines, Tesla proposed a craft with an electrically charged hull that would reduce air resistance and enable unprecedented speeds. The concept involved creating a strong electrical field around the aircraft that would ionize the surrounding air, potentially creating a path of less resistance through which the craft could move. While the full details of Tesla's propulsion system remain unclear, the concept represents his thinking about how electrical forces might be harnessed for revolutionary transportation methods. Given the technological limitations of his era, Tesla's supersonic airship remained theoretical. However, modern research into electroaerodynamic propulsion, sometimes called ionic wind technology, has demonstrated that electrically charged surfaces can indeed generate thrust without moving parts, suggesting Tesla's concept contained elements of genuine scientific insight. While we haven't realized Tesla's vision of electrically powered supersonic flight, his idea represents another example of his willingness to consider radically different approaches to engineering challenges rather than incrementally improving existing technologies. VTOL aircraft design. In the early 1910s, Tesla conceptualized aircraft capable of vertical takeoff and landing, VTOL, decades before such vehicles became practical reality. While conventional aircraft of the era required long runways for takeoff and landing, Tesla envisioned more versatile flying machines that could rise straight up from the ground. His designs combined elements of helicopter and fixed-wing aircraft, with propulsion systems that could direct thrust downward for takeoff and landing, then redirect it horizontally for forward flight. This fundamental approach, thrust vectoring, remains central to modern VTOL aircraft, like the Harrier jet and V-22 Osprey. Tesla understood that VTOL capability would dramatically expand the utility of aircraft, allowing them to operate from small spaces in urban areas or unimproved terrain without airports. This insight proved prescient, as VTOL technology has indeed become crucial for military applications, search and rescue operations, and urban air mobility concepts. Though the technology of Tesla's time couldn't realize his VTOL concepts, his vision accurately anticipated a direction that aeronautical engineering would eventually take. Today's developing urban air taxi services and next-generation VTOL aircraft represent the fulfillment of a vision Tesla articulated more than a century ago. Fliver aircraft. In the 1910s, as automobiles were beginning to transform American life, Tesla was already thinking beyond road transportation. He designed what he called a fliver aircraft, a small, affordable flying machine intended for personal transportation, conceptually parallel to Ford's Model T automobile that was making car ownership accessible to ordinary Americans. Tesla believed that personal aircraft would eventually become as common as automobiles, fundamentally changing how people traveled and where they could live. His fliver aircraft designs emphasized simplicity, safety, and ease of operation, qualities essential for any technology intended for widespread adoption. While personal aircraft never achieved the ubiquity Tesla envisioned, his concept anticipated important developments in aviation. Today's growing interest in personal air vehicles, ultralight aircraft, and urban air mobility solutions suggests Tesla may have been prescient about the direction of transportation technology, even if his timeline was optimistic. The dream of personal flight that Tesla articulated continues to inspire aviation innovators today, with modern electric vertical takeoff and landing eVTOL designs potentially bringing us closer to Tesla's vision of accessible personal air transportation. Electromagnetic propulsion systems. Throughout the 1910s and 1920s, Tesla worked on theoretical designs for electromagnetic propulsion systems that would move vehicles without conventional engines. Rather than combustion or jet propulsion, these systems would use electromagnetic fields to generate thrust. This wasn't merely speculative thinking. Tesla had already demonstrated the practical application of electromagnetic principles in his induction motor and other devices. His propulsion concepts extended these principles to create motion without moving parts or traditional fuel combustion. While specific details of Tesla's electromagnetic propulsion designs remain limited, the concept aligns with his lifelong interest in harnessing electromagnetic forces for practical applications. Modern research into electromagnetic propulsion systems, from railguns to experimental space drive concepts, suggests Tesla was once again thinking decades ahead of his contemporaries. Imagine traveling in a vehicle with no roaring engines, no exhaust fumes, and no mechanical vibrations, just the quiet hum of electromagnetic fields propelling you forward. Tesla envisioned transportation systems that would be cleaner, more reliable, and potentially faster than anything powered by conventional engines. Today we're seeing glimpses of Tesla's vision in technologies like maglev trains that use electromagnetic repulsion to float above their tracks, eliminating friction and enabling speeds over 300 miles per hour. More experimental concepts like plasma thrusters for spacecraft and electromagnetic aircraft propulsion systems continue this line of inquiry that Tesla began over a century ago. Anti-gravity research. Throughout his later years, Tesla alluded to research into what he sometimes called anti-gravity effects. These weren't the fanciful anti-gravity devices of science fiction, but rather serious investigations into how electromagnetic fields might counteract or modify gravitational effects. Tesla understood gravity differently than mainstream physics of his time. He viewed gravitational forces as potentially related to electromagnetic phenomena, a perspective that was unorthodox then and remains outside conventional physics today. Nevertheless, his explorations in this area demonstrated his willingness to question fundamental assumptions about the physical world. In his notes and occasional interviews, Tesla suggested he had observed unusual effects during his high-voltage experiments, objects exhibiting reduced weight or unusual movement patterns when subjected to certain electromagnetic conditions. While skeptics dismissed these claims, Tesla maintained he had identified principles that could eventually lead to practical applications. Think about how revolutionary this concept would be if realized. Imagine construction equipment that could effortlessly lift massive components, vehicles that could hover without conventional propulsion, or entirely new modes of transportation freed from surface friction. These were the kinds of possibilities Tesla envisioned from his theoretical work. While we haven't achieved true anti-gravity technology in the conventional sense, modern physics has indeed revealed complex relationships between fundamental forces that weren't understood in Tesla's time. His intuition that gravity might be manipulated through electromagnetic means, while not validated in the way he imagined, represented the kind of boundary-pushing thought that defines scientific visionaries. Dynamic theory of gravity. From the 1890s until his death, Tesla worked intermittently on what he called his dynamic theory of gravity, an alternative explanation for gravitational force that he believed would revolutionize physics. Unlike Einstein's geometric theory of gravity, which describes it as a curvature of space-time, Tesla's approach sought to explain gravity as a field phenomenon related to electromagnetic forces. Tesla's theory was never published in complete form, but fragments from his notes and interviews suggest he believed gravity resulted from specific actions of the ether, the theoretical medium that many 19th century scientists believed pervaded all space and its interactions with matter and energy. He claimed his theory would unify gravitational and electromagnetic phenomena under a single explanatory framework. To appreciate the significance of this pursuit, consider the context. Tesla was working during a revolutionary period in physics. Einstein's theories of relativity were transforming our understanding of space, time, and gravity, while quantum mechanics was beginning to reveal the strange behavior of matter at atomic scales. In this environment of fundamental reassessment, Tesla was proposing yet another radical perspective. While Tesla's dynamic theory of gravity never gained mainstream scientific acceptance, and the concept of the ether was eventually abandoned by physics, his intuition that fundamental forces might be unified was prescient. Modern physics continues to search for a unified field theory that would bring together all fundamental forces, a goal that Tesla pursued in his own way a century ago. His work reminds us that even unsuccessful scientific explorations can represent important contributions to human knowledge by encouraging us to question established understandings. The Teleforce weapon, death ray. One of Tesla's most controversial later concepts was what the press sensationally dubbed the death ray, though Tesla himself preferred the more technical term teleforce. In the 1930s, during rising international tensions that would lead to World War II, Tesla announced he was developing a defensive weapon system so powerful it would make war obsolete by ensuring mutual vulnerability. The Teleforce weapon wasn't a ray in the traditional science fiction sense. Rather, Tesla described it as an accelerated particle beam technology that would project concentrated energy over great distances. He claimed it could generate particles with such tremendous kinetic energy that they could bring down fleets of aircraft from hundreds of miles away. Tesla explained that his device would accelerate microscopic particles of mercury to high velocities through electrostatic repulsion, creating a beam that could penetrate enormous distances through the atmosphere with minimal dispersion. The power requirements would be substantial but manageable with his electrical transmission technology. Imagine the impact such a technology would have had in the pre-nuclear age of the 1930s, a defensive weapon that could strike at vast distances without explosives, potentially rendering traditional military assets obsolete. Tesla believed this technology would create a defensive capability so overwhelming that nations would be forced to abandon warfare entirely. While Tesla claimed to have developed working prototypes, no definitive proof of a functioning Teleforce weapon was ever demonstrated publicly. After his death in 1943, various military agencies reportedly examined his papers, but found no complete plans for such a device. Nevertheless, the concept Tesla proposed bears some resemblance to directed energy weapons and particle beam concepts that military researchers would seriously explore decades later. Modern defensive systems like the experimental free electron laser represent technological descendants of the kind of directed energy weapon Tesla envisioned. Directed energy shield. Complementing his Teleforce weapon concept, Tesla also proposed what we might now call a directed energy shield, a defensive technology that could deflect or neutralize incoming projectiles using concentrated energy fields. This was less fully developed than his offensive Teleforce concept, but represented part of his integrated vision for defensive technology. Tesla suggested that the same principles underlying his particle beam weapon could be adapted to create protective energy fields around sensitive targets. These fields would disrupt incoming projectiles through intense electromagnetic effects or direct particle interactions. Consider how revolutionary such technology would be if realized. Cities protected by invisible shields rather than physical barriers, rendering conventional artillery and bombing attacks ineffective. Tesla believed such defensive capabilities would fundamentally alter the strategic balance between offense and defense in warfare, potentially making aggression futile. While Tesla's specific directed energy shield concept hasn't been realized as he envisioned, modern military technology has indeed moved toward active defense systems that intercept incoming threats with directed energy. Today's developmental laser-based missile defense systems, while functioning differently than Tesla's concept, serve the similar purpose of creating a protective capability against projectile weapons. Tesla's vision of energy-based defensive systems highlights his understanding that technological development often makes previous military doctrines obsolete, a pattern that continues to shape international security in our own time. Atmospheric electricity harvesting. Throughout his career, Tesla was fascinated by the electricity naturally present in Earth's atmosphere. In his later years, he devoted considerable effort to developing methods for harvesting this ambient energy as a power source. The atmosphere maintains an electrical potential difference relative to the ground, strongest during thunderstorms but present even in fair weather, that Tesla believed could be tapped for practical use. Tesla designed special collectors to capture atmospheric electricity, experimenting with elevated conductors that could accumulate electrical charge from the air. He envisioned networks of these collectors providing electricity without fuel or complicated generating equipment, essentially harvesting energy that was already present in our environment. Imagine the implications if this vision had been fully realized. Distributed electrical power generation without fuel costs or pollution, available virtually anywhere on Earth. Tesla believed this atmospheric electricity could eventually provide abundant clean energy for humanity's needs, supplementing or even replacing conventional power sources. While Tesla's specific atmospheric electricity harvesting systems never achieved commercial viability, the concept of capturing ambient environmental energy hasn't disappeared. Modern research into harvesting atmospheric potential difference continues, though primarily for low-power applications. More broadly, Tesla's vision of harvesting energy from the environment has been realized through solar, wind, and other renewable technologies that tap into natural energy flows around us. Tesla's pursuit of atmospheric electricity represents his lifelong pattern of looking beyond conventional approaches to identify untapped energy sources that others had overlooked. Resonant extraction of Earth's energy. During his famous Colorado Springs experiments in 1899, Tesla explored what he called the resonant extraction of Earth's energy, a method for tapping into the planet's electromagnetic field by creating systems tuned to its natural frequencies. Tesla believed the Earth itself was an enormous reservoir of electrical energy that could be accessed through properly designed resonant circuits. His approach involved creating electrical oscillations that matched the natural frequency of the Earth's electrical system, similar to how pushing a swing at just the right moment builds powerful motion from small inputs. By establishing resonance between his equipment and the planet's electromagnetic field, Tesla claimed he could extract substantial energy with minimal input. Consider what this would mean if successful. Virtually unlimited electrical power available anywhere on Earth without fuel, pollution, or extensive infrastructure. Tesla believed this resonant energy extraction could eventually provide abundant electricity for all of humanity's needs, a vision of clean, universal energy access that remains compelling today. While conventional science has not validated Tesla's specific claims about resonant extraction of Earth's energy, his work touched on genuine phenomena that continue to interest researchers. The Earth does maintain electromagnetic resonances, now called Schumann resonances, and energy harvesting through resonant principles has valid applications in modern technology, though typically at much smaller scales than Tesla envisioned. Tesla's work on resonant energy extraction represented his characteristic approach to looking beyond obvious energy sources to identify subtle physical phenomena with potential practical applications, an approach that continues to inspire unconventional energy research today. Radiant energy collector. In his later years, Tesla worked on devices he called radiant energy collectors, systems designed to capture ambient energy from the environment in forms beyond just atmospheric electricity. These collectors were intended to harness various forms of background radiation and convert them into usable electrical power. Unlike conventional power generation that relies on concentrated energy sources like fuel or falling water, Tesla's radiant energy systems sought to collect the diffuse energy present everywhere in our environment, from solar radiation to cosmic rays to thermal differentials. The key innovation in Tesla's approach was developing materials and circuits sensitive enough to accumulate these typically overlooked energy forms in useful quantities. Imagine having devices that could continuously generate electricity without fuel, moving parts, or appreciable maintenance, simply by harvesting energy from the environment around them. Tesla envisioned a future where such collectors might provide distributed power generation for homes and communities without centralized infrastructure. While Tesla's specific radiant energy collectors didn't achieve commercial success in his lifetime, his vision anticipated important developments in modern energy technology. Today's photovoltaic solar panels, thermoelectric generators, and other ambient energy harvesting technologies embody the same fundamental concept Tesla pursued, converting naturally occurring environmental energy into usable electricity. The principle behind Tesla's radiant energy collectors, that useful energy exists all around us if we can develop appropriate means to capture it, remains an important insight driving renewable energy development and distributed power generation research today. Self-acting engine. Among Tesla's more theoretical later concepts was what he called the self-acting engine, a device designed to convert small ambient temperature fluctuations into continuous mechanical motion. Unlike conventional heat engines that require significant temperature differences to operate efficiently, Tesla's concept aimed to extract useful work from the subtle temperature variations naturally occurring in our environment. The operational principle involved a sophisticated arrangement of materials with different thermal properties that would respond to minute temperature changes by producing mechanical movement. Tesla believed these small movements could be accumulated and amplified to generate useful power without conventional fuel inputs. Consider the revolutionary nature of such a device if successfully developed. Engines that would run continuously without fuel, powered solely by the natural temperature variations in their surroundings. Tesla envisioned these engines potentially providing perpetual motion within the practical limitations of real-world physics, not violating thermodynamic laws but cleverly exploiting natural energy fluctuations that conventional approaches ignored. While Tesla's self-acting engine concept never reached practical implementation in his lifetime, the underlying principle of harvesting energy from ambient temperature differentials has found limited application in modern thermoelectric generators. These devices, though typically requiring larger temperature differences than Tesla envisioned exploiting, convert thermal gradients directly into electricity without moving parts. Tesla's pursuit of the self-acting engine exemplifies his persistent interest in identifying overlooked energy sources in our environment, an approach that continues to inspire research into ambient energy harvesting and low-impact power generation technologies today. Cosmic ray motor. In his later interviews and writings, Tesla proposed one of his most speculative energy concepts, a motor powered by cosmic radiation. He theorized that high-energy particles constantly bombarding Earth from space could be harnessed to generate electricity through properly designed collection and conversion systems. Cosmic rays, primarily high-energy protons and atomic nuclei from beyond our solar system, continuously strike Earth's atmosphere, creating cascades of secondary particles. Tesla believed these energetic particles represented an untapped power source that could be collected and converted to usable energy through specialized materials and circuits. Imagine the implications of successfully developing such technology. Power generation unaffected by weather, time of day, or location, constantly producing electricity from the invisible rain of particles from space. Tesla envisioned cosmic ray motors potentially providing reliable power in remote locations or serving as supplementary energy sources that would operate continuously regardless of environmental conditions. While Tesla's specific cosmic ray motor concept hasn't been realized as he envisioned, modern science has confirmed his basic observation that significant energy exists in cosmic radiation. However, the practical challenges of efficiently collecting this diffuse energy have prevented commercial development of cosmic ray power generation. Nevertheless, the concept demonstrates Tesla's characteristic approach of looking beyond conventional energy sources to identify fundamental physical phenomena with potential practical applications. Tesla's cosmic ray motor concept represents the kind of boundary-pushing thinking that, while not always immediately practical, expands our conception of what might eventually be possible as our technological capabilities advance. The thought camera. Among Tesla's most speculative later concepts was what he called the thought camera, a theoretical device for recording mental imagery directly from the brain. In interviews during the 1930s, Tesla described his belief that thoughts had physical correlates in the form of specific brain activity patterns that might be detected and recorded by sufficiently sensitive equipment. Tesla's concept went beyond simple brain activity monitoring. He theorized that the specific images and ideas in a person's mind produced distinctive electromagnetic patterns that, if properly detected and processed, could be reconstructed into visual form, effectively photographing thoughts. While he claimed to have conducted preliminary experiments in this direction, no working thought camera was ever demonstrated. Consider how revolutionary such technology would be if realized: direct communication of mental imagery without the limitations of language, new understanding of cognitive processes, and profound implications for art, education, and human communication. Tesla's thought camera concept anticipated later scientific interest in brain-computer interfaces by many decades. While we haven't achieved anything approaching Tesla's specific vision of thought photography, modern neuroscience has made remarkable progress in brain imaging and neural activity decoding. Today's functional MRI and electroencephalography can identify broad patterns of brain activity associated with specific thoughts, and rudimentary image reconstruction from brain activity has been demonstrated in research settings, suggesting Tesla's intuition about the physical basis of mental imagery wasn't entirely unfounded. Tesla's speculation about thought recording technology represents his willingness to explore the boundaries between established science and seemingly impossible possibilities, an approach that continues to characterize pioneering research in brain-computer interface technology today. Thought transmission technology. Complementing his thought camera concept, Tesla also speculated about the possibility of direct mind-to-mind communication through technological means. In writings on consciousness and the brain, Tesla suggested that the electrical patterns of one person's thoughts might be captured, transmitted, and reproduced in another person's brain, creating a form of technologically mediated telepathy. Tesla viewed the brain primarily as an electrical system, with thoughts representing specific patterns of electrical activity. If these patterns could be precisely recorded and reproduced, he reasoned, it might be possible to transmit thoughts directly between individuals without the limitations and potential misunderstandings of language-based communication. Imagine the profound implications if such technology were realized: direct sharing of experiences, emotions, and ideas without the filters and limitations of language. New forms of human connection and understanding across linguistic and cultural boundaries, and potentially revolutionary approaches to education, where knowledge might be transferred more directly than through conventional teaching methods. While Tesla's specific vision of technological thought transmission hasn't been achieved, modern brain-computer interface research has made initial steps in related directions. Experimental systems allowing limited brain-to-brain communication through computer intermediaries have been demonstrated in laboratory settings, and commercial research into neural interfaces continues to advance. Tesla's speculation about thought transmission technology, while far ahead of the technical capabilities of his time, demonstrates his characteristic approach of looking beyond conventional assumptions about what technology might eventually achieve, an approach that continues to inspire cutting-edge research in neurotechnology today. Bioenergetic healing devices. Building on his earlier work with high-frequency currents and his interest in the electrical nature of biological systems, Tesla experimented with various electrical devices intended for therapeutic medical applications in his later years. These bioenergetic healing devices used carefully controlled electrical frequencies that Tesla believed could promote healing through direct electrical stimulation of the body's tissues and systems. Tesla approached this work with the same scientific rigor he applied to his engineering projects, carefully studying the effects of different electrical frequencies, waveforms, and application methods on biological systems. He believed that many health problems stemmed from electrical imbalances or disruptions in the body's natural bioelectrical processes, issues that might be addressed through precisely calibrated electrical stimulation. Imagine medical treatment that worked directly with the body's electrical systems to promote natural healing processes, potentially addressing causes rather than merely managing symptoms. Tesla envisioned electrical therapies that might eventually complement or even replace certain pharmaceutical and surgical interventions, offering less invasive approaches to supporting health and treating disease. While many of Tesla's specific therapeutic claims would require modern clinical validation, his intuition about the importance of bioelectrical processes in health wasn't unfounded. Today, various legitimate electrotherapy approaches are used in mainstream medicine, from transcutaneous electrical nerve stimulation, TENS, for pain management to electrical stimulation for wound healing and bone growth. Modern research continues to explore bioelectrical aspects of cellular function and healing processes, suggesting Tesla's general direction of inquiry had merit, even if some of his specific approaches and claims remain unverified. Tesla's work on bioenergetic healing devices demonstrates his willingness to apply his electrical expertise across disciplinary boundaries. In this case, bridging engineering and medicine in ways that anticipated later developments in biomedical engineering. Weather modification technology. One of Tesla's most controversial claims involved the potential for technological weather modification using powerful electromagnetic effects. Based on observations during his Colorado Springs experiments, where he generated enormous electrical discharges, Tesla claimed his equipment had affected weather patterns in the surrounding area. He later suggested that properly designed electromagnetic systems might eventually offer deliberate control over certain weather phenomena. Tesla's weather modification concepts weren't about small-scale effects, but potentially global-scale influence on atmospheric conditions. He theorized that sufficiently powerful and precisely tuned electromagnetic impulses might trigger changes in the ionosphere and other atmospheric layers, potentially influencing precipitation patterns, storm formation, or other meteorological processes. Consider the implications if such technology were perfected: the ability to bring rainfall to drought-stricken regions, divert destructive storms from populated areas, or potentially mitigate extreme weather events associated with climate change. Tesla envisioned controlled weather modification as a beneficial technology that could address significant human challenges related to agricultural productivity and natural disaster prevention. While Tesla's specific weather modification claims remain unverified by modern standards, research into electromagnetic influences on atmospheric processes continues in various forms today. Programs like HAARP, High Frequency Active Auroral Research Program, have studied how radio energy in the ionosphere might affect weather-related processes, though with far more modest claims than Tesla made about his own work. Tesla's speculations about technological weather modification, while controversial, represent his characteristic approach to considering how powerful technological interventions might address large-scale human challenges, an approach that continues to inspire both mainstream research and speculative inquiry into geoengineering possibilities today. Oscillator-based seismograph. Alongside his more famous mechanical oscillator experiments in the 1890s, Tesla developed sensitive instruments for detecting and measuring Earth vibrations, essentially creating an early form of seismograph based on oscillation principles. These devices used mechanical resonance to amplify small ground movements, making them detectable and measurable with the technology of the time. Tesla's oscillator-based seismograph was more than just a measuring instrument. It represented an application of his deep understanding of resonance phenomena to earth science. By creating mechanical systems that would resonate in response to specific frequencies of ground vibration, Tesla could detect subtle seismic activity that might be missed by less sensitive instruments. Imagine having precise early warning of seismic events or enhanced ability to study Earth's internal processes through more sensitive detection of ground movements. Tesla believed improved seismic monitoring could both advance scientific understanding of Earth's structure and potentially provide practical benefits through better prediction of earthquakes and other geological events. While Tesla's specific seismograph designs didn't become the standard in the field, his work contributed to the development of more sensitive seismic detection technology during a formative period in seismology. Modern seismographs, while using different specific mechanisms, still rely on principles of carefully calibrated sensitivity to ground movements that Tesla explored in his oscillator-based designs. Tesla's work on seismic detection demonstrates his ability to apply principles developed in one field, electrical and mechanical oscillation, to challenges in seemingly unrelated areas, geological monitoring, a cross-disciplinary approach characteristic of his wide-ranging scientific interests. Hydroelectric power at Niagara Falls. The final entry in our exploration of Tesla's innovations brings us to one of his most enduring practical achievements, the implementation of large-scale hydroelectric power at Niagara Falls. While not solely Tesla's project, the Niagara Falls power plant represented the first major commercial application of his polyphase AC electrical system and a turning point in the adoption of alternating current technology. In 1895, after years of planning and construction, the Niagara Falls Power Company began operating the world's first major hydroelectric alternating current power plant. The system used Tesla's polyphase designs and was built by Westinghouse Electric using Tesla's patents. Initially, the plant powered local industry, but in November 1896 the system began transmitting power to Buffalo, New York, some 22 miles away, demonstrating the long-distance transmission capabilities that made Tesla's AC system so revolutionary. Consider the historical significance of this achievement. Niagara Falls had long symbolized natural power and majesty. Harnessing its energy for practical use represented humanity's growing technological capability. More importantly, the success of the Niagara project definitively settled the war of currents in favor of Tesla's AC system, establishing the technological foundation for modern electrical power distribution worldwide. The Niagara Falls installation wasn't just another power plant. It was a proof of concept for renewable energy on an unprecedented scale. By demonstrating that natural water power could be converted to electricity and transmitted efficiently over significant distances, the project established a model for sustainable power generation that continues to influence our approach to energy production today. While Tesla's name isn't always prominently associated with the Niagara project in popular accounts, engineering historians recognize it as perhaps the most significant practical implementation of his electrical system designs, an achievement that transformed not just American industry but global approaches to electrical power generation and distribution. The generators at Niagara Falls have been updated and replaced over the decades, but hydroelectric power continues to be generated at this site more than a century later, producing clean, renewable energy using the same fundamental principles Tesla helped establish in the 1890s. Few technological systems can claim such lasting practical impact and continued relevance. Our journey through Tesla's extraordinary inventions and concepts reveals a mind that consistently worked beyond the boundaries of conventional thinking. From practical innovations that power our world today to theoretical concepts that continue to inspire cutting-edge research, Tesla's legacy extends far beyond his historically recognized achievements. What makes Tesla's work so remarkable isn't just his prolific output or technical brilliance, but his unique approach to problem-solving. Where others sought incremental improvements to existing technologies, Tesla often reimagined fundamentals, asking not, "How can we make this better?" but "Is there an entirely different way to approach this challenge?" His vision extended from practical engineering to speculative science, from industrial applications to theoretical physics, from mechanical devices to global systems. Some of his concepts proved immediately practical and transformative, others remained theoretical or ahead of their time, and still others continue to inspire debate about their feasibility and implications. Perhaps Tesla's greatest legacy isn't any single invention, but his approach to innovation itself, a willingness to question fundamental assumptions, envision radically different possibilities, and pursue ambitious ideas despite skepticism or limited resources. In an age of specialization, Tesla worked across disciplines, seeing connections and possibilities that specialists might miss. As we continue developing technologies to address contemporary challenges from sustainable energy to climate change, from medical treatment to transportation, Tesla's legacy offers an important reminder. The most transformative solutions often come not from refining what already exists, but from reimagining what might be possible. In that spirit of audacious innovation, Nikola Tesla remains not just a historical figure, but a continuing inspiration for those working at the frontiers of science and technology today.